All right. If you think it is trapped air, raise your hand. Okay? If you think it is some other molecule besides air, raise your hand. If you think it's empty space, nothing at all, raise your hand. Answer? Nothing at all!
Then why is it red?
Okay,
My answer too
so
then. What the hell?
this is oxygen. This is hydrogen, oxygen, hydrogen, hydrogen. There's nothing in between. What weighs more, air or nothing? Nothing. Or air weighs more than nothing. What weighs more? Air. Nothing weighs very little. So, what weighs more, air or nothing? Air. Okay. So, and what is air? Air is O2 and N2 primarily. How big would an O2 molecule be in here? Very big. There's no space for air in there. There's no space for air in that molecule. It's empty space. Nothing weighs less than air.
Whoa.
Yeah.
So is that why you didn't push it? No, I haven't already yet, but I already have to push my favorite. So.
Okay. The next type of force is really goofy. I'm not a big fan of it because people get confused. It takes, you have to focus, you have to concentrate. Are you concentrating?
I am.
Okay, so what we've talked about so far, polar molecules are attracted to polar molecules, like little magnets. If I took a bunch of these BBs, which are not magnetic, and I threw them out on the gym floor, are they gonna stick?
No.
No. But here's the thing about non-polar molecules. Non-polar molecules, like carbon dioxide, and everybody's favorite, nitrogen. Nitrogen is a triple bond like so. If these things get cold enough, something very strange happens. The electrons are moving back and forth, right? Yes. Are there any bond dipoles here? No. There's no bond dipoles, so it's a completely non-polar molecule. But something very strange happens because we know we can liquefy nitrogen. Okay? We can take gaseous nitrogen, cool it down to about -80, -90 Celsius, and it will liquefy. How? Magic. No, close. Accio liquefaction. How do we liquefy nitrogen? If nitrogen is a non-polar molecule, how do we liquefy it? You have to get it cold, but how does that make it liquefy? If I liquefy... Yep. So how does slowing down all these molecules make it condense? Okay. This is going to represent the electron. In fact, this is going to represent the electrons, plural, in the nitrogen molecule. Anna, or Aaron, catch. Okay. Hand that to Matthew. Matthew, hand it back to Aaron. Hand it back to Matthew. Hand it back to Aaron. Hand it back to Matthew. Hand it back to Aaron. Now, pretend you're extremely cold.
Energy.
How fast? Yeah, yes. He's moving very, very slowly. So the idea is this. If the molecule gets cold enough, that exchange of electrons becomes so slow that all of a sudden, for just a tiny instance, that nitrogen now has more of the electron density than that nitrogen. And how would you describe a molecule where one atom has more electronegative density than the other one? Polar. So are you concentrating? Yes. So what happens in a non-polar molecule, this is the only thing that happens in a non-polar molecule, when they get really, really, really cold, the electrons exchange so slowly that all of a sudden, for weird reasons, one atom now has a polar side, a partial negative side. And once that happens, that partial negativeness just basically shoots through all the molecules. It causes other molecules to become polar. That's a process called polarization. Kind of like what happens when a magnet picks up a paperclip. The paperclip's not magnetic, but the magnet makes it magnetic. So if a molecule, for reasons that we don't entirely understand, if it gets slow enough, that non-polar molecule becomes slightly polar for just a tiny millisecond and causes a bunch of neighboring molecules to become polar, and they'll stick together. Okay? This was proposed by a guy named London. So we call them London forces. Yes?
Is that like when the balloon sticks to the wall?
No. That's static electricity, but that is polarization. But it's a little bit different. When a balloon sticks to the wall, balloons, the rubber in balloons like to take electrons, and hair likes to give up electrons.
Yeah.
So you rub the balloon and your hair transfers the electrons to the balloon, and the balloon becomes negatively charged.
And that's why it stays to your head.
Yep. Because liquid nitrogen wants to be a gas. It's constantly warming up. All right. So does this make sense? By the way, I do have to mention this. You might hear these called van der Waals forces instead of a guy. So basically, a guy named London. They weren't discovered inland. A guy named London came up with the London forces, and another guy named van der Waal came up with a similar force. At your level of education, until you get to physical chemistry, your third year in college, they're the same thing. At your level. We're going to call them London forces because that's easier to remember. But they're very similar to van der Waals. They're basically similar. Okay, does that make sense?
Yeah.
So, in summary, there's a battle between physical properties or there's a battle between intermolecular forces and kinetic energy for physical properties. Stronger attraction. If you have stronger attracting molecules, do you have a higher boiling point or a lower boiling point?
Higher.
Higher. More attraction, more energy needed to break. Stronger attraction, higher melting point. More attraction, more energy needed to break. What about density? Chat with your neighbor. If you have, let's go back to this guy. Which of these is more dense? The polar or the superpolar? Which is more dense?
Superpolar. Aaron, the ball's falling. Aaron, the ball just fell.
He's okay. All right. If you believe polar is more dense than superpolar, raise your hand. If you believe superpolar is more dense than polar, raise your hand. You'd be right. Because if you're more polar, then your molecules are pulled closer together. Water, you might know, is extremely dense. Did you know water is extremely dense?
Extremely.
It is extremely dense. Almost every other liquid floats on water. It's extremely dense. Because water is extremely polar. Okay. So, can you summarize the battle of intermolecular forces and kinetic energy for solids, liquids, and gases? For a solid, what wins?
Wouldn't it be the ice?
Should be IMF, not IF, but in solids, what wins? The intermolecular forces. In solids, the intermolecular forces are stronger than the kinetic energy. Does that make sense? As you increase the kinetic energy, eventually they start to win. And the kinetic energy starts winning, and what happens? It turns into a liquid. Liquids exist when the kinetic energy is about the same as the intermolecular forces. Okay? When there's a good balance between intermolecular forces that want to hold the molecules together and kinetic energy that want to have the molecules move apart, you get a liquid. And if you keep raising the temperature and you keep increasing the kinetic energy, what does that liquid become? A gas. A gas exists when the kinetic energy beats the intermolecular forces. Does that make sense? Now, good? Okay, now we're going to revisit this. Guys, I realize you don't want to hear me talk. I don't really want to talk either, but I do need to get through this. We're going to revisit this in the spring too, when we do states of matter and what we call solid, liquid, gas equilibrium. But right now, just realize that there is a battle between intermolecular forces and kinetic energy. When the kinetic energy is winning, you get a gas. When the intermolecular forces are winning, you get a solid. And how do you change gas? How do you change states between a solid and a liquid? You increase the what? You increase the kinetic energy. How do you turn a liquid into a solid?
Decrease the kinetic energy.
Decrease the kinetic energy. How do you turn a gas into a solid?
Liquid.
Decrease the kinetic energy. Carbon dioxide goes right. Carbon dioxide at room at normal temperature or normal pressures skips the liquid phase altogether. All right, how are we doing? Because we're about to change gears.
Oh, okay.
Be nice.
Okay, now for this next step, you will need a little bit of paper. So if you don't have paper in front of you, borrow one from a neighbor.
Is there a way to get?
Okay. So there was this dude named Lewis, and he said, you know what? There's really no standard way to draw atoms and molecules, so I'm going to come up with one. And the dude was a genius. He basically said, since what we are pursuing are octets, let's make a system where atoms are shown with their valence electrons around the atom. And what we came up with is this thing called Lewis structures, or Lewis dot structures. A Lewis dot structure is shown with an atom and the number of valence electrons it has around it. Okay? So if I had 2 valence electrons, I would be like, here's atom me, 1 valence electron, 2 valence electrons. And I would carry my valence electrons around with me. It's a lot easier than showing this as an atom. It's like this with oxygen, but only the outer shell. Make sense?
Yep.
Now, I will tell you, some people draw Lewis structures differently. I always do it the exact same way, and I found it to work really well, especially if you're going to move on to other college or AP level chemistry. Start at the top and move around. I'll show you what I mean. So, chlorine. How many valence electrons does chlorine have? Chilling out in group 17, it has 7. You would show these like this. 1, 2, 3, 4, 5, 6, 7. So, show you again. You start at the top, and you go clockwise around the atom until you've run out of electrons. Okay? So you start like this. 1, 2, 3, 4, 5, 6, 7. Now, making little e's is going to take a long time. So Lewis thought, rather than show them as e's, let's show them as dots. So instead of e's, we go 1, 2, 3, 4, 5, 6, 7. Dots are easier than e's. E's take a long time to draw. So let's use dots. 1, 2, 3, 4, 5, 6, 7. Make sense? So if that model makes sense to you, if you wouldn't mind, please show, or please practice showing oxygen. So start at O, figure out how many valence electrons oxygen has, and then put them as dots around your little O.
No, 8.
I'm sorry?
8.
Is that what your neighbor thinks?
Isn't it 8? Oh, 6. We think 6.
Valence electrons. So start at the top and put them around in order, one electron at a time, clockwise. So your first dot is going to go up top. There's 1. There's 2. There's 3. There's 4. There's 5. And there's 6. Okay. This shows us a pretty easy way to say, hey, oxygen's got 2 places it can bond. It needs 2 more electrons to fill its outer shell. Okay? These double electrons have special names. They're called lone pairs or unshared pairs. And the single dots are bonding electrons that are going to form bonding pairs. So these are the rules. And we're going to practice this for the next 12 minutes. So the double dots are called lone pairs or unshared pairs. to always call them unshared pairs, but then I hear lone pairs coming up more and more often. So you pick. I'll use them interchangeably. Sometimes I'll call them lone pairs. Sometimes I'll call them unshared pairs. And then the single dots are bonding electrons. They're the ones that get the job done. All right. Questions? Are you feeling good about this? Okay. Here's an animation I made about 17 years ago. Back when Word had really rough animations, and I never bothered to fix it. So we're going to do methane. So methane's a pretty common molecule. It's a non-polar gas at room temperature. It's very handy. You can dissolve all sorts of fun stuff in it, like methyl mercaptan, which is the stinky part of farts. You can't smell methane, by the way. Methane's also about a third natural gas. Kind of fun. So what you first need to do is identify what atoms are present. What elements are present in methane? Well, you got a carbon and 4 hydrogens. Then you have to identify how many valence electrons are present and put dots around the atom based on the number of valence electrons. So go ahead and give that a try. How many valence electrons does hydrogen have? 1. How many does carbon have? 4. So then we just put the dots around the atom. Carbon gets 4, 1, 2, 3, 4, and hydrogen gets 1 each. Okay, again, carbon gets 4, 1, 2, 3, 4, and hydrogen gets 1 each. Once you've got the dots, you just move the atoms around like Legos until everything has an octet except hydrogen. How many does hydrogen need to fill its shell? 2. So here's my bad animation. So I move my carbon down, and I move my hydrogen over. That carbon's happy, that hydrogen's happy, that hydrogen's happy, that hydrogen's happy, and this hydrogen is happy. Hey look, carbon now has a full octet, and hydrogen has a dutet. Or a dostet, or a tutet. I don't even know what it's called. It's a tutet. We'll call it a tutet. Okay. Then you show bonding pairs with sticks. This is what you usually think of in chemistry. You're like, I see lots of letters and sticks to connect them. That is methane.
So if it's double bonded, then it's just a line?
If it's double bonded, you'll have 2 lines. You'll have 4 dots if it's double bonded.
Oh, okay.
So, does this make sense to you?
Yes.
Then it should make sense if you have your oxygen right here and a pair of hydrogens. So you have a hydrogen here and a hydrogen here. It should make sense that if you put one hydrogen there and the other hydrogen there, you get Can you see oxygen's unshared pairs? And then the bonding pairs that became sticks, and then we just turned it 45 degrees to make it look cool. That's all we did. So we made water. It's like this, and we turned it 45 degrees to make it look cool. Yeah. Yeah, exactly. Okay. Now the thing about unshared pairs. Unshared pairs are, listen carefully. Unshared pairs are, in this class, unshared. Unshared pairs are, in this class, unshared. Which is why I like to call them unshared pairs and not lone pairs. Now, when you move on to chemistry AP or college level chemistry, then you will encounter situations where unshared pairs can be broken up and become shared pairs. But in this class, unshared pairs stay unshared pairs. Capiche? So if oxygen starts with 2 unshared pairs, how many it's going to end with? 2. Cool. All right. So if that makes sense to you, we have 7 minutes. Whoa, okay. Hold on. One at a time. There we go. Okay. On your paper, I'm going to turn the lights on. Please practice these. And we'll come back tomorrow and we'll check our work.